So this is guidelines for evaluating a study, and this could help you in that project. Um, so these are just some rough things. So like, even if you were arguing with your friend, so I have a friend named Josh, and he he is he's very nice and he's very smart, but he's kind of the opposite politically as far as me. So we argue a lot about political things, and I always send him studies, and he always sends me studies to help support his point. And we probably need better hobbies, but I always, whenever he sends me a study or like a post or like some article or something that he's like, this is why it is. Um, you do use some of these techniques even in just kind of a common day or everyday sort of like, oh, I'm trying to argue with this person thing. Maybe you don't do that. But you know what, so you kind of go through this list, and it's not like it's not like you go through this, there's an order. The order doesn't really matter. You're just kind of looking for things that stand out. So for instance, you know, bias in the researchers. As far as your project goes with, if assuming you're using Kleck and Hemingway, again, feel free to use other authors if you have a paper that supports your position. Just make sure you have at least two that are opposing. You know, so as far as Kleck and Hemingway go, I don't know if they have much bias. Hemingway is they're both professors. I haven't looked in. You can look into if they've gotten like any. My head's cut off. If they've gotten you know, like money from, you know, like maybe I haven't Googled it, but maybe Kleck has gotten funding from like the NRA or something, or maybe Hemingway has gotten funding from some anti-gun group. You never know. So you could look into their funding. I kind of doubt that either of them has any issues bias-wise, but you never know. Because as I said, they're both professors. Usually professors that, like, you know, do have conflicts of interest, but they get money from the university and stuff like
What
that.
page are you on?
Oh, this is the last page of the notes. I forgot about it, so I put it in the end. Because if I put it in the front, I'd have to reformat everything. So sorry. Yep. So look for bias in researchers. You never know. Look for bias in the sample. This is the big one. Bias in the sample. Usually, if there's going to be an issue in a study, it's going to be in the sample being biased in some way, or four here. Three, I guess more like three. Problems in measuring the data or analyzing it. So, or analyzing. Right. So if you have problems in the sample, you know, sometimes you'll see studies that have really small sample sizes. So, and this is something you can look for in even like news articles you see, like you'll see like news articles that say like, oh, coffee is good for you, or coffee is bad for you, or both. And you'll look at the sample and it's like 34 kids or something, not children, but 34 people. And so it's very small. Usually you want as big of a sample as possible, assuming you're studying people. And you know, small samples are not ideal. So if you see a study and it looks really legit, but their sample size is like 2 people, it doesn't make any sense. So things like that. You can also look for, you know, how do they choose their sample? We've talked about this a lot in the one class, but where's their sample from? You know, so if you look at Kleck's paper, let me see if I have it over here. Kleck's paper, so it's this one. His sample, and it's a long paper, but I advise you to at least read the intro. I don't know if I have it noted here, but here we are, the methods. So the methods, so this is on page 160 in Kleck's paper, but they describe how they did the study. So again, skim around the paper. Usually when you see when you're trying to read a paper, you kind of skim through it real quick first, read the introduction, skim through each subsection, and kind of get an idea of what the outline of the paper is. And then you read into whatever section you need to understand the most. So for your purposes, the methods will be important. In particular, like here, you'll read, so they did a anonymous random digit dial telephone survey. They did not know the identities of those interviewed, and they had people interview, Yep, so we interviewed a large number covering ages 18 and over in the lower 48s, living in households with telephones, all right? And they described really everything in pretty good detail. So like if you read through it, you'll see like we inquired about uses of both handguns and other types of guns, and they're trying to be as specific as possible. Like they excluded occupational uses of guns and uses against animals. So they're even like, you know, if you're out on a walk in Montana and you bring your pistol with you for defense, like against a bear, they're not going to count that in their study. They're interested in like human on human self-defense. So they're making that pretty clear. And they really go into detail. They used a professional telephone polling firm, and you know, so these are all things you can talk about in your paper when you're looking either if you're supporting or against Kleck. You can try to point out issues, or you can point out how well he did, depending. And again, there's no right or wrong answer here. They're both studies that were peer reviewed and published, so they're at least at some level of correctness. And yeah, so you know, there shouldn't be too much. There's some of the language might be a little complicated, but there isn't a lot that we haven't covered really. They don't use, at least in the methods, any sophisticated like techniques or anything. They're just describing what they do. And yeah, so again, that's one way you can look at it. So look at the method. So in his case, it's a randomized telephone survey done by a professional polling firm. They don't list the firm, but it's assumed to be something legit. So you could find bias in that, you could not find bias. So as an example of how you could find bias in that, if you read Hemingway's paper, he has a lovely example. I guess, I don't know the date, maybe it was like 94, 96, but there was a randomized telephone poll put out, and it asked people, have you experienced aliens, or have you seen aliens, or something to that effect. And it was an alarming amount of people on this randomized telephone poll said that they have seen or like had an experience with aliens or extraterrestrials. So like his point was that you could use randomized telephone surveys to prove a lot of things that don't necessarily extrapolate to the population at large. I think it was like 6% or something. He said of the people he polled said that they had experiences with extraterrestrials. And so if you were to extrapolate that to the population at large, right, there's 328 million Americans. So if you say that 6% of them have seen UFOs or have actually had UFO experiences, so that means that there are almost 20 million. There are almost 20 million UFO encounters every year, right? So his argument is that this is a defensive gun use. Hemingway's arguing is a rare event, and so studying it like UFOs with a telephone survey isn't effective because people will kind of say crazy things on the telephone, essentially, or say incorrect things on the telephone. So that's how Hemingway would argue against Kleck as far as his sample. He'd say that the sample screwed up, telephone surveys can give you weird results. And there you go. But yeah, it's you're arguing it. So just kind of lay out what your points are. And then problems in measuring the variables and data. I don't remember exactly how Kleck did his, but you can go through and see if anything is screwy. I don't think you'll find anything. Again, this is a Kleck, they're both peer-reviewed papers. So you probably won't find too much wrong with how he measured the variables of data. Maybe, if anything, you'll say, are the questions biased? Questions biased? All right, so maybe he asked some questions that weren't quite up to snuff, or maybe some of his questions were leading, or maybe maybe the question itself is biased because it's a rare event and people are going to overestimate how often they've used their gun in self-defense. You know, and it's also hard to say if you use it in self-defense, right? So if you're at a bar and you have like a pistol, a sidearm or something, and like an open carry, and you get into an argument with a guy, you could argue that you used it in self-defense just by having it on your side, because maybe the other guy saw your gun and was like, oh, I'm not going to fight you or something. And so, you know, you're leaving this judgment up to the person you're calling. So that could even be a problem. So again, it is your decision. And then the last, make sure they're fairly presented. You know, if their data says one thing, but they're trying to spin it in another way, then it's not going to be correct, even though their data is correct. They're presenting it in an odd way. So that kind of thing. Again, this probably won't be as much problem. For both of these, really 2 and 3 are probably your bread and butter. Right. Anyway, any questions? Any questions about this paper thing? Nope. All right. So again, feel free to let me know if you have any issues with writing it or if you have any questions about the papers themselves. If you try to read them, let me know. Again, the collect is kind of long. Hemingway should be fine, but you have like a week and a half. Okay. All right. Anyway, let's get to some actual stuff that we need. So there we are. All right. So observational studies are studies. Let me zoom some. There we go. Our studies which conclusions are drawn from observation. So everything we've talked about thus far has been observation, really. Like you're not doing anything to the population. Like you're looking up, you're asking them questions, you're about what they've done. You're sometimes if you like CLEC and Hemingway both use this national crime database, you're using databases to compile numbers and data and then derive statistics from that database data. And things like that. So you're not really doing an experiment. You're not doing any action to a sample of people. You're just asking them what they do. So that's called an observational study. So anyone can do one, really. As I said, you can poll people about anything. It doesn't really cost you. I mean, it costs you money to run the poll, I suppose, like asking people, but it doesn't cost you a lot as far as experiments go. All right, so that's the kind we've been talking about. In contrast, an experiment is a study where you're doing something, like you're testing a new vaccine. So like you're giving a COVID vaccine to 10,000 people, and then you're studying their health for the next, a year or 6 months or whatever it is, and seeing if they get COVID or if they die from COVID. And any vaccines, same kind of way. You could be studying a malaria vaccine, and sometimes what they'll do to study a new vaccine. So like, if they're studying if they have a new malaria vaccine and you'll take two people, there are two groups of people, and you'll give one the old vaccine and you'll give one the new vaccine and see how they compare. Right? So that your action there is that you're giving someone a vaccine or a medicine or a treatment.
There.
Huh?
I took a psychology class this semester, and you also have to have a third group of people that don't get any vaccine at all.
Oh yeah, like a control. Yeah, and you have a control.
Yeah, that way that people can't say it's biased.
Yeah. Although I've read, I'm not an expert in statistics or like scientific or vaccines, but I've read that sometimes they can't, like, are there ethical concerns about not giving someone a vaccine? Like if you're in Africa doing a trial on malaria, is it ethical to not give a control group a vaccine? I don't know.
I mean, I guess it all depends on, like, you have to put in the thing saying, like, this person will get this person will get that, and then
Yeah.
so like the person has to sign this saying this is all the risks.
Yeah.
And then if they are agreeing with it, then they're
huh.
agreeing with it.
Interesting. I know. So this is a huge topic, and there's a whole I know there's like if you go into like nursing or medical fields, there's like classes on ethics. So it's a whole thing, and even I know that math, we don't do experiments like this where we actually deal with people. So it's not really a problem in math. But I did a research program when I was an undergraduate, and we had to do this like research ethics course that was just required by the university as like a thing. And it was all like, don't do bad things to your people, and like it's very complicated, I will say. And I don't know, luckily math doesn't do that. If you go into a field that does use people in your studies, it's not easy. But yeah, anyway, experiment, the important part, you have a treatment, right? That's the distinction. And here's some more examples. Drop a ball 100 times from like the top of a stairwell and see how high it bounces and record the data. Your treatment there is dropping the ball. And then new shampoo, your treatment in this case is you're trying the shampoo on your head and seeing how it works. And you can just do it over and over again. So you don't always need 1 million people to do a sample. All right, so let's try this one. So determine which is observational and which is an experiment. Right. And if it's an experiment, you want to identify what you're doing, like what the treatment is, it's called. So like what the action that you're performing is, and studying. So the weights of 30 random people are measured. Anything? Observation or experiment?
Observational.
Yep. You're just measuring observation. Subject are asked to do 20 jumping jacks, and then their heart rates are measured.
Experiment.
That one would be an experiment because you're asking them, the treatment is you're telling them to do jumping jacks. So I would say
The
that's
way
it.
I think of it is you're testing something.
Yeah. Yeah. Yeah, exactly. You're testing something. In this case, their heart's doing jumping jacks, but it can be anything. And the last one, 20 people are given a concentration test after drinking a cup of coffee.
Experiment.
I would say it's experiment too. Yeah. Sometimes it can be like in a middle ground, but I would say experiment for those two. All right, and again, so the treatment here in this last one would be drinking a cup of coffee and then doing a test. Although I guess drinking the cup of coffee is the treatment, so I'll say that's treatment. For this one, the second one, it would be the jumping jacks, right? And then you're measuring. So you do a treatment and you measure. You do a treatment, the coffee, and you measure the test. So, all right. Let's see. All right. Oh, and we sort of talked about this with the vaccines, but an experiment will often have a control group and a treatment group. All right. So the control group will get nothing, the control. So they don't get the treatment, and then the treatment group obviously gets the treatment. And the reason you need these two groups, right, is if you're testing something and you only do it to everyone, then you don't know what happens when you don't do it. So, if you're testing a new medication or something and you just give it to all your people in your study, and you don't give it to, and there's no one that doesn't get it, then you don't know what happens when they don't. You know what I mean? You can't really judge the effect of something unless you see what isn't happening or what's not.
They're not getting anything, or it says the control group is getting a sample but not getting the treatment. So are they getting a fake treatment?
Yeah, they can be getting a fake treatment. So we'll talk about that actually at the bottom of this page. But in effect, they're not getting any treatment. The control group should get nothing. So that's what I should have. Yeah, not getting the treatment. All right. So in this case, you want to test new malaria medication. How would you set up your experiment? Who would be in your control and treatment? So you basically just want to identify. So like we already talked about this a little bit. So it's kind of a bad example, but your control here would be people not getting the medication. People not getting medication. And as I said, the other thing you could do is give them an old medication. You could give, maybe you're bringing a new malaria medication to market and you want to see how your new malaria medication compares to the current malaria medication. So you could also give them that. So give them an older medication. All right, so that way they're still protected against malaria. So they're not all going to die, because we all know that they need something to protect them from malaria. So they're not going to die, but you're going to see if yours is worse or better. And it will change the study if you give them another medication, right? It's going to change it in the effect that you're not studying your medication versus no medication. It changes it in that you're comparing the two medications now, if that makes sense. So you're kind of basing yours on this other, which does work, because we know how some medications already work. So, and the treatment will be the one that's getting it. So this is the sample getting the medication. All right. And then you would give them it, not give them it, or give them a different one, and then you would just see, in this case, it's something medical. So you watch these people and see how their health progresses, and it will depend. The same friend I was telling you about, who's arguing with me, sent me some malaria vaccination study the one day, and in that study they were comparing it to an older malaria medication, But so what they did is they gave the treatment, they gave the control, the old medication, and they kept track of these people for, I don't know, I forget what it was, a few years, I think. And they just observed all the effects that occurred. And what happens is that, some effects will not be related to the medication, but you have to note them. So like in this particular study, it was on it was on thousands of people, and they had like 5 people who had seizures that came for a few months and then left and never came back. So they had to note that in their study, and they said that 5 people had seizures. Most of them just went away brief, and they were brief episodes. But you'll have things like that, and so the majority of people didn't have seizures, but you have to keep watch and see all the different effects that could be related to your treatment, and take it into consideration. All right. And like Destiny was saying, the placebo effect is when the effectiveness of the treatment. So basically, if you're in the control group and you're not getting a treatment, your results might differ, right? So like, for instance, if I give you a sugar pill and say this is like, I don't know, something special, like it's going to protect you from COVID or something. And you take this sugar pill, you might think, oh, it's really going to protect me. And sometimes it apparently works. I don't understand how exactly it works, but sometimes the placebo effect is such that you can actually cause beneficial health things just by thinking you're taking a pill, even though you're not. And I have no idea why that works. But
It's because your brain fights off whatever it's coming there because you're not thinking, oh, I have this, oh, I have that. So your immune system's actually kicking in like it's supposed to. So
really,
like when we first got COVID, like there
yeah.
were so many people out because they didn't feel good and our rate spiked. But then after a couple of weeks, everybody's like, oh no, I don't got COVID. And then everything stopped.
Weird.
Like weird.
Yeah. The placebo effect is a real thing. So basically what they have to do to get to kind of negate that effect is, if you're in the control group, they'll give you, like, if it's a pill, they'll give you a fake pill and you won't know the difference. So you'll just be taking it not knowing what group you're in. The researchers might know what group you're in, but you don't. And so this effect won't be as pronounced, I guess. Just because you don't know what group you're in. So you kind of could be well there. So that's the placebo effect. All right. And speaking of knowing who was in which group, a blind study is one in which you don't know where you are. You could be in the control, you can be in the treatment, you don't know. A double-blind study is one in which no one knows. I mean, someone does, but the researchers don't know. Again, some researchers do, but the researchers don't know who is in which control group. And you might think that a double-blind study is a little excessive, but the example I have below will kind of help demonstrate why you might need a double-blind study. At the very least, you have to have a blind study, because if you know what group you're in, your results might differ just by the placebo effect or something. So a blind study is like the bare minimum. Sometimes you need a double-blind. And here's an example where you might, right? So well, this one is, but so what's wrong with these experiments? The first experiment, a doctor does a treatment on 25 patients with all positive results. He concludes the treatment's effective. So what could be the problem with this first study?
No control group.
There's no control group, right? So like, he didn't do it, he did it to all of his patients and they all had this effect. So you don't know what would happen if he didn't do it. Like he might have been doing nothing to these people and they might just feel better because he's a doctor doing something to them. So they're like, oh, I feel better. But in reality, it might just be the placebo effect. They might go in for a treatment, get the treatment, and feel better purely because it's a treatment. So you don't know. You need to control. All right. Without a control group, you don't know if you're actually doing anything. All right. So that's the first big problem. And the second one here is a little more setup. So you have a medicine you give medicine given to some children, and you have some in the control, and you have some in the treatment group. And the doctors, after some period of having this medication, the doctors interview each of the kids. And so the doctors know who was in each group. So it's only a blind study. It's only a blind study. It's not a double blind study. So the doctors know who is in each group. Um, and after the treatment, they interview them, the kids. So what could be the problem with this? So it might be a little not clear. But the problem is that the doctors are interviewing the children and the doctors know who's in each group. So what could happen, and it might even be a subconscious thing, it might not be a conscious effort by the doctors to manipulate the study. It could be, but it might not be.
Like
It's more,
slip up and tell them that they're in the like
well,
study group or not study group.
well, it could even be something as like innocent as just the tone of their voice. You know, like if you're interviewing a student or a child and you know that they're in the treatment group, you're just the tone of your voice, you might be more encouraging to hear these good results. Like you might just, again, it might be totally innocent on the part of the researchers, but they might be really happy to hear that this person is getting good results if they know they're in the treatment group. And so they might be more encouraging if they're directly interviewing them, or even the tone of their voice might be more optimistic or happy or something. Um, Versus someone when they're interviewing the control group. When they interview the control group, they know they're not getting any medications. So they might not even waste their time um, fully getting out all of the things that they're feeling. And so they might miss they might kind of skew things one way or the other. So that's the problem. It's because they're interviewing. They're interviewing the children and they know what group they're in. Again, it's mostly subconscious. I think that's mostly the problem. I think by and large, we assume doctors are trustworthy, not to, although it does happen. But I mean, I would like to imagine a world where most doctors doing research aren't trying to screw up their own their study. All right. All right. Any questions with that? So again, it's kind of subtle, but that's why double-blind study is important. All right. All right. And this, I should have talked about this before, but for some reason in the book, it's in 10.5. It's confounding. A confounding variable is a variable that you don't want to study. And so, as I said, doing studies is wildly complicated, and they have whole classes on them if you go into like medical things. But so a confounding variable is you want to study one variable, but this variable is in the background, kind of changing things for you. So you might be trying to study one thing, but in reality, you might be studying a slew of things. So here's an example. I should have given myself more space for this example. It's okay. So this example, you want to find the differences in different types of elm trees. So apparently there are different like species of elm trees or something. I'm not an arborist, but there's different types of elm trees. And you want to see if certain types of elm trees are more resilient to insect damage. So what you do is you find 20 of these trees and it's a random sampling, like maybe you've documented every elm tree in Olean and you go around and you list where they are and you list the type and then you take 20 random ones. And what you do is you go and inspect them for insect damage. Maybe you take a core, maybe you just look at the tree and give it a number and gauge it. But somehow you list the status of this tree and you quantify the insect damage on this tree. There. And then you figure out which trees are more resilient to insect damage by just seeing which species of elm tree did better in your measuring. All right. So it seems like a nice enough study, but there's problems. And so what could be some confounding variables? And again, so confounding here, we want to study the insect damage, and we want to study it relative to the species of elm tree. But what variables might we be missing if we just look at random trees?
Different types of bugs in different areas.
Yeah. So if you're talking about a very tiny area, you probably have the same bugs, but you don't know. You could be talking about all of Western New York or all of the state of New York, even if you're a big enough arborist, you might be doing a study nationwide even. So you have to be careful. Different types of bugs, different types bugs. Yeah, that's great. What else do we have? What other like confounding variables? What other things might be
Weather.
weather, right? So a tree in a valley is going to be very different from a tree up on a hill or mountain, or a tree in a rural area might have a very different experience weather-wise than a tree like in a city, right? So weather. What else?
I
You
was
have,
gonna say sunlight, but sunlight doesn't really have that falls under weather, I would say.
I would say so too. But like basically like where the tree is, right? Like
Location.
location, that's a better way to say that. Location. Um, and not even like generally location, like specifically where it is. Like, is it often in the shadow? Is it in a very hot location? Is it get a lot of direct sunlight? Things like that. And another thing you could even consider is it maintained? Like maintenance. Like, does it get some kind of fertilizer, antifungal stuff? Is it being pruned? Is it being taken care of? Is it a wild elm tree? There's a ton of different variables. So you have to like this would seem like a good study, but what you probably end up with is just a list of the elm trees that are the best taken care of, not so much the species of elm trees that are most resilient to insects. Um, so if you really wanted to study which species of elm trees are more resilient, what you'd really have to do is you'd have to plant elm trees of each species and kind of have like make sure they each get very similar as much as you can conditions. You'd want to make sure that they're in the same sort of place with the same sort of soil. Soil is another one. Um, and you want to make sure they get similar weather. They're in a similar like elevation where it's not too cold and not too warm relative to the other trees. There's a whole bunch of things you have to like control if you wanted to study this. And I think people do that actually. I think arborists probably they look at trees from similar kind of locations with similar features. But yeah, so that those are all confounding variables, right? Really anything that can sway your result that isn't what you want to study. Right? Questions? Okay. All right. So that's 10-4. Just kind of basic experiment study kind of definitions. So 10-5, as I said, is kind of short. It's all about just categorizing some data. So categorical data. I would usually call it qualitative, but the book calls it categorical, whatever floats your boat. Our piece of information, they're not numerical generally. So like, what color are your eyes? Or what zip code do you live in, kind of thing. They're things that you can't like if you have a list of people's eye colors, you can't find the average, right? I mean, you could figure out which occurs most, but you couldn't like, you know, unless you gave them a number somehow to average, you couldn't find averages. Um, like ages. If you took a list of ages from a group of people, you could average them together and get an exact average, like it's a number. But with eye color, can't do much, right? So that's qualitative. Quantitative response is that as opposite. It's numbers. They're numbers. Anything that and not even just numbers. So you'd be careful. Like as I said, zip codes are numbers, but they're not quantitative because you can't do stuff with them. You can't like add them or subtract them. They're just haphazardly distributed across the United States. You can't do math with them. You can't analyze them in the same way. So they would fall under categorical or qualitative. Anything like that would be qualitative. Like phone numbers, same kind of thing. You can't do anything with a phone number. The numbers don't really mean anything. It's just an address essentially. So, all right. So here's an example. And this is just what I talked about. If you ask people for their age, you'll have quantitative again because you can do math with those numbers. If you ask them how they feel about being their age, you'll have qualitative. So like on a scale, I guess that would be bad. Like, do you feel happy? Do you feel happy about being 64, or do you feel sad about being 27? If you ask them how they feel about being their age, that's qualitative. You can put it in like categories or bins. But so let's just categorize these. Qualitative or quantitative? Zip codes we already talked about. Qualitative, right? Because again, you can't do math with them. They do have meaning, but I have no idea what they mean. I don't really know how it works. So, but you can't average zip codes. Really, if you ever question if it's qualitative or quantitative, just ask yourself if you can average it. If you can average it, it's going to be quantitative. If you can't average it, it's not. Eye color, qualitative. Again, what you could do it was kind of interesting though, is that eye color isn't numbers, right? But what you could do almost is you could, like, if you assigned each eye color like a number, you could kind of average those together. But that's not what we're talking about. But that you could do that. And so again, all of this is kind of fluid. High temperature over several weeks. What's that one going to be? It's a bunch of numbers, right? And they average temperatures all the time. So we're going to say quantitative. And then income, again, you can add, subtract, average, manipulate, otherwise analyze income. So that's also quantitative. Cool. So, so as I said, 10.5 goes by as fast. There's not much in 10.5. I don't know why it's its own section. It's just categorizing data into two camps, all right? So, but 10.6 is more interesting. 10.6 is all about graphs, and most of us probably have seen most of these graphs before. So let me find my sheet here. And as a result, there's not a lot of notes here. So we're gonna fill it in. So we're gonna do an example. Also, I'm sorry, my hands, they're so dry. Everything's so dry. I wash my hands like 30 times a day. It's not a compulsion. It's that I have a sink in my room and it's the whole thing. So suppose we have some grades, right? Suppose you just taught a class at JCC and you've compiled your grades and they are as follows. So suppose you have the grades, right? So I don't know, A, B, F, F, D, C, 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 B, A, B. Right. So, what we're talking about frequency tables here. So, a frequency table is some of these things, if I gave you this data, you might just make these things up on your own. You might not need someone to tell you what they are. But a frequency table is you just see how many times each appears, right? So if I do grade and then a frequency, and I guess I'll put a line. It doesn't matter, right? And so you just list all the grades. A, B, C, D, no E. I will never understand why E is not a thing. And then F. And some places don't have A pluses. I don't know if anyone has A pluses. Grading schemes are so different everywhere you go. It's very odd. But you use count. So, sorry. 1A, 2A, there's two A's. There's two A's. So you put 2 for the frequency. And you count the B's. 1, 2, 3. 3 B's. Group. C, you count the C's. 1, 2, 3. And you count the D's. 1 D, just 1 D. And then F's, 2 F's. There you go. I don't know what this is like. I guess this is relatively normal. There's usually a lot of C's, some D's, a lot of B's. And then depending on the class, there's some F's, a good number of F's sometimes. And yeah, and so this is a frequency table. As I said, it's something you would have made just by yourself if you were given the data, I'm sure. All right, but what we can do, what's more interesting too, is we can compute the relative frequencies. All right, so the relative frequencies are just going to be the percentage of grades in each category. All right, and this whole thing, this whole table business has nothing to do with grades. So you could do this for any data you have, any list of data, and it would have to be categorical data. Like, so these are categorical. I'll put that up here. All right, so this works for categorical data, where you put your data in categories or bins. So like my A's are like a category, my B's are a category, my C's are a category, so on and so forth. If you had like the number grades, it'd be a little weird because you can't count the number grades as well, right? Because like, do you count a 96.1 the same as a 96.2? Do you count an 89.8 the same as an 89.3? Like, where's the cutoffs exactly? And once you choose those cutoffs, you've recovered these letter grades. So this sort of system works only really with categorical data. All right. Anyway, so the percentage. Sorry
about that. What about a farmer? Like, would that be considered categorical? Like how many bovines, how many horses?
Oh yeah, yep. Yeah, totally. Like if you're a farmer and you have cows, horses, goats, and whatnot, and you count up each of those as a category. So you'd have cows number, goats number, whatever, and you could even like have like subcategories if you like. I know there are different kinds of cows, so you could have different like subcategories for each cow and tally it up and do the same thing. Yeah. So grades, cows, or anything that fits in a category. You could do categories, categories of categories. It's all very exciting. Anyway, so the percentage of grades you need categories. So for instance, for A, I have a total, so maybe I'll put total over here, forgot that. I have a total of how many grades? I guess I'm gonna just add these up. 5, 11. I have 11 grades total. And so there are 2 A's. So I would have 2 over 11. And most of the time we like that as a percent. So times 100. 2 divided by 11. Oh, well, you can't see that. It's not on. So there's a bunch of problems there. There we go. 2 divided by 11 times 100. So it's about 18%. All right. And you would say this is the relative frequency. Right. And relative frequency makes sense, right? This is the frequency, 2 is the frequency of A, but relative to the whole, it's 2 out of 11. So the name fits perfectly what you were describing. And you can do the rest. Let me get another sheet of paper. So for B, so for B, you have 3 out of 11. So times 100 again to get it as a percent. And I already did this one. It's about 27%. Again, relative frequency. Oops, sorry about that. There you go. You can do the same for C. There are 3 C's. So it's going to be the same 3 over 11. And then times 100 is again 27%, give or take. D. What do we have? We had 1D, so 1 out of 11 times 100, and so you're just doing the same thing on your calculator, right? 1 over 100 or 1 over 11, sorry, times 100. So it's about 9%. And I'm rounding. You can be as precise as you like. And then last but not least, the F's, my favorite category of categories, 2 out of 11, which is again just like A, 18%. All right. So these relative frequencies, the way you'd read it is you have 18% had A's, 18% had F's, 27% had both C's and B's, and then 9% had a D, right? And you can make these up for any class size. If you're in like a, what should happen is if, generally speaking, generally, any class will have about the same makeup of A, B's, C's, D's, and F's. So like if you're in a 140 person lecture hall at UB and you take your grades and make a relative frequency list, you'll have about the same percentages as you would in like a small like 20-person class at JCC. So it's just how it works. But yeah, all right. So any questions with frequency tables or relative frequency tables? I don't know how much of a table this is, but these are called relative frequencies. All right, so the next thing we want to talk about is related. And we'll use the same data, so I will keep it nearby so I don't lose it. All right, so, oh wait, we forgot one thing. What is it? Oh, let me talk about this too. So the one thing we can do too, again, there's all sorts of analysis you can do here, but the one thing you can do is called cumulative frequencies. Oops, sorry, cumulative frequencies. Okay. And so this, for instance, so what percentage of students got at least a C? All right, so you want to find the students that did C and above. So what you do is you go to your chart that we just compiled. Sorry, there we go. And you want the C's and above. So you'll have 27% got C's. Ooh, put this in. So 27. And you have 27% getting B's, so plus 27. And then you have 18% getting A's, so plus 18. So 72% of the people in this class got C or above. So you can just add them up. So it's going to be 27% plus 27% plus 18%. So 72%. Right? The other way you could do it is, everything's rounded, but the other way you could do it too is you could count the number of people who got those grades initially and then just divide that by 11. So you'll have 2, 3, and 3 over 11. And then just times 100. Right? So either way you think about it, it probably makes more sense just to add the percentages up because we've already computed them. But in a situation where you hadn't computed the percentages, you can also just find the number of people who got C and above and divide it by the total. Right? So those are cumulative. And it's cumulative only because it's combining categories. All right. Yeah. All right. Sorry. So that was a little side thing. Now we can get in to bar graphs. All right. Where are my bar graphs? Here we are. All right. So let's make a bar graph for the one we just did. And again, most everyone has done bar graphs before at some point in their life. Might have been like a decade or two ago, but everyone has done them at some point. So I'll rewrite my letters, my grades, just so we have them. Oh, actually, I'll just bring my frequency table down. All right, so this is our frequency table. And so to make a bar graph, what we're going to do is each category, in this case, my letter grades, will be a bar. And the height of the bar will be the frequency. Right. So I'll just write each category is a bar whose height is the frequency of that category. Right. So for instance, we'll move it up a little more. In our situation, we have A, B, C, D, and it's like on an XY plane, but it's not really in an XY plane. It's just a table. So we have A, and what's the order? The order doesn't matter. A, B, C, D, and no E but F. And the heights, so our grade frequencies range between 1 and 3. So we don't really need to get very complicated. 1, 2, 3 maybe. Right? And you just put the bar where it is. So A's, there were 2 A's, so I'll put A up to 2. And you can make them touch. They don't have to touch. Doesn't really matter. I'll make mine touch. There were 3 B's, so this will be kind of fat. There you go. Microsoft Word can do this. There'll be 3 C's. There were 1 D, so the D will be down here. And then there were 2 F's, so these are back up here. It's not a very pretty bar graph, but it's a bar graph. Yeah, so it's just another way of presenting frequency tables. Basically, regardless of how you're presenting it, all your data will always come down to a frequency table or a relative frequency table. And you can just present them in different ways. So this is a presentation of a frequency table, just each category with the number of things in that category. And the other thing you can do for your relative frequencies is present it as a pie chart, which everyone loves, right? I love pie in all of its forms. The number, the edible thing, and charts. So for the chart, what we'll do is we'll just draw pi, or circle, also known as a pie. And what we're going to do here is we're going to present the relative frequencies in a different way. So, and the reason we're using a pi for the relative frequencies, if it's not clear, is that the relative frequencies are all percentages, right? They're all out of 100. So the way you want to think about it is that your pi is the 100. The whole thing is 100%. And what we're doing is we're taking little snippets of it to represent the relative frequencies of each of our grades. So for instance, we said that 18% were A's. So I'll put like a little blooper there. And I don't know, it's not gonna be very accurate, but A's. So I'll put 18%. And then my B's was 27%. So 27 is just over a quarter. So maybe like, again, not very accurate. Like there, B, 27%. All right. And then the C's were also 27%. And then we've got D's were only 9. So those are like a little blooper. It's okay. It's not quite right, but you understand. 9%. And then my F's are too big, but it's okay. My F's, 18%. These should be bigger. It's okay. But yeah, so that's my pie chart. Pie chart for relative frequencies. All right, so you wouldn't do a pie chart for just the frequencies because it doesn't really make any sense. Like the whole reason you're doing a pie chart, as I said, is because the whole thing represents 100%. If you're doing it, well, I guess you could do it like, it's just kind of weird. Like the way you could do it with the frequencies would be like, this would be 2, this would be 3, 3, 1, and 2. But then the whole pie would be 11. It's just a little weird. There's something inherently wrong with it. It's just a little funky. But it's usually used for relative frequencies just for that reason. It's just kind of awkward unless you're doing percentages. Right? And again, anything that's categorical in nature, anything where you have categories of data and you just like eye colors, you could do all of this for eye colors. Just tally up the eye colors in a room and you could do the same thing. Anything, it's super broad. All right, and then do I have any more? I think we have more. Yes, the last kind of chart to talk about, histograms and line charts. Again, people usually have seen these things, but let's do a histogram first. They're a little funky, not as used. For the histogram, looks like an A. For the histogram, it's essentially a pie chart, or not a pie chart, a bar graph. But the difference is that instead of putting things categorically or qualitatively, we're putting them quantitatively. So it's going to look just like a bar graph. So let me draw this like this. Bloop, bloop, bloop. There we go. All right, and let me get my bar graph. So this was a bar graph, and it's going to look just like that, except it's going to have numbers in the bottom. So let me list the grades. So 90 to 100 is A. And then every 10 we'll say is a letter grade just to make our lives simple. So we'll say 50 to 60 Let me put how many boxes do I need? I need 1, 2, 3, 4, 5. I need 5 boxes. So 1, 2, 3, 4, 5. All right. So I have 5 little boxes. So 50 to 60 would be my like F. And then 60 to 70 would be my C's. 70 to 80. Oh no, D's, sorry. And this would be my D's. And then 70 to 80 is my C's. 80 to 90 is my B's. And 90 to 100 are my A's. All right. So as far as this course goes, if you're interested, I kind of stretch them a little. So, and you know, if you have like an 89.6, you have a 90, which is an A. So I kind of stretch and try to give you the best chance to get a better grade. But this is just making things simple. Anyway, and then you just put the data in. So we have the same number, the same frequencies, 1, 2, 3. All right, and you just plop things in. So my F's, I had 2 F's. I had 1 D. I had 3 of both B's and C's. And I had 2 of the A's. All right. So a histogram is usually used for qualitative data, not quantitative data, sorry. Things that aren't in categories. So you can list like a range. Yeah, so quantitative data. All right. So like you wouldn't, you know, if, I don't know, if you had zip codes, for instance, you wouldn't do a histogram because you can't really list zip codes. You could put them in bins. So you could categorically, you could do like zip codes on a bar graph because you just put like zip codes at the bottom. But you wouldn't put zip codes like this, like on a number line, because it doesn't make sense. So this would be more for quantitative, things that make sense like on a number line. And the last one, a line chart, is very close to this. It's really just another presentation of it. So a line chart, it's just a variation on a histogram. So what I'll do is I'll start with the same scale. So I have 50, 60, 70, 80, 90, 100. And then each range is our letter grade. And we have the same frequencies. Those don't really change. But instead of making a bar, I'm just gonna put a dot. So I'm gonna put, you know, I had 2 F's, so I'll put a dot there. And I'll put it right in the middle. You can put wherever, as long as you're consistent. And then we had 3 B's and 3 C's. So I'll put a 3 up here, and then another 3 up here for the C's. And then I had 1 D, so I'll go down here. Oh, wait a minute. Oh, I'm sorry. I put my dot in the wrong place. I always forget D. I don't know why. It's down here. And then I'll put a dot up here. I'll figure it out in the end. There we go. That one doesn't exist. And then I had 2 F's. So I'll put it, or 2 A's. Goodness gracious. I'm reading it backwards. There we go. All right. And then you connect the dots. So boop, 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 boop. All right, so that'd be my line chart for my grades. A line chart makes more sense when you're looking for some kind of progression almost. So like if you were a nurse and you had a bunch of heartbeats from a patient over a period of time, you could put them on a line chart, because then what you can see is you can see the heartbeat going up and down, and you can see like the variations and the trends in the heart rate. But for grades like this, like going up on the grade scale doesn't really mean anything as far as the test scores go. Like you're not looking for a pattern there. So for different charts are usually used for different purposes, and a line chart, not so much for grade. You just use a bar graph or a bar graph for your chart. Like that first one we did. For the grades, this would probably be ideal. If you have cows or goats, something like this would also be ideal. This really anything with time would be great for a line chart like that, because you can see how things are kind of progressing as time goes on. But here it doesn't really make sense to use a line chart. Same with a histogram. You can use a histogram, this is fine, but it makes more sense to use a bar graph. Okay. So any questions about all of that? No? All right. I think that's it for now. Let's see. So next class, we'll finish the chapter. We only have 2 sections, and we can answer any questions. Feel free to bring questions about the project or that assessment. But yeah, we'll finish chapter 10 next class, and then the 15th will be the test review, and then that week we'll have the test. You'll do the test at some point, and we'll be done. So yeah, there we go. All right. If you have any questions, let me know. But otherwise, I'll see you on Thursday.
Yeah, I did have a question here, Matt.
Yeah.